Section 10.8, Laplace's equation. So there are two versions we're going to consider. One is 2 dimensions, and the other one dimensions. So we're 2-dimensional. We're going to do second partial derivatives of both u and x. Add those together, we get 0. For 3 dimensions, we're going to repeat this. So we're going to add z's in. Our Laplace's equation is sometimes called the potential function, or the potential equation. And that's because it satisfies text box, expand. There we go. Satisfies the potential of a particle free space by forces. So since it satisfies the potential function, it's called the potential equation, or potential function, same thing. No other place you'll see this used is heat conduction. With our alpha squared uxx uyy equals u tt. Let me make sure that those letters actually look like x's and y's. That's going to be first derivative, not second. And now if this is in steady state, so whenever we kind of reach a, I don't call it equilibrium. We don't have any variation. You set into a repetitive pattern. Steady state, where we do reach a steady state where we don't have change. That whole thing is going to equal 0 because time will not make a difference in our steady state. Other areas, the warping function, where displacements, which gives displacements when a perfectly elastic bar is twisted. We also have velocity, the velocity and stroke function. Here, we have steady, which is time independent. And I can no longer get the text box to spread out. There we go. Time independent, two-dimensional, inviscid, rotational motion of an incompressible fluid. So it's steady. So, all right, time doesn't make any difference in this. It's two-dimensional, so we can go left, right, front, back. In viscid fluid, it's not going to flow, so we can't have stuff moving through the liquid, or it doesn't move. Irrotational, if I can spell motion, so it's not going to move. Incompressible fluid, so fluid stuff doesn't flow through it. It can't be compressed. Not going to rotate, so we have a almost pretty much like a solid type deal. Other thing, I can change color, so we're talking about different things. The Dirichlet now this is first boundary problem of and it's a problem. And let me go here. Laplace's equation with boundary values. And specifically, we'll look at the Dirichlet problem for a rectangle. So with this, two dimensions, and given our boundaries, at 0, we're going to equal 0. And at B, we're going to equal 0. That's going to be for an x between 0 and some a value. And we're also going to have u of x y equals 0 and u of a y equals 0 for y between some 0 and b. So if you think of this being graphed, you have a there, we have b up there. We're seeing what's happening on this rectangle. And at each of these corners, oops, almost. That's not equal to 0. That's equal to some function of y. So whenever y equals 0 and x varies, so along this whole side is 0, along that whole side is 0, along this whole side is 0. And then over here it equals some function of y. And then in the middle, we have our second derivative of x when plus second derivative of y equals 0. And so whenever we solve this, just like before, we can assume it's separable. And we have our setup here. Make that u look a little bit better. And then if we rewrite this, we get that. And then since we can separate it, should be an equal sign, not a plus. And this lambda is going to be our separation constant again. So if we go to solve these equations, down to there, and here our x is going to be between our 0 and a, and our y will be between 0 and b. Now, depending on our given conditions, for this one, our x naught is going to be 0. Our y naught is going to be 0. And our y at b is going to be 0. If we look back at our setup here, whenever x is 0, whenever y is 0, whenever y is b, we had these three sides were all 0. So that's another way to represent it. And kind of like what we had with our other setups, we'll have a non-trivial solution only for lambda equaling n pi over b all squared, where n is a natural number. If I can draw a natural number symbol really nicely. And so when we get this, or for these values, we're going to get this. But for those initial conditions, our K1 is going to equal 0. Let's get rid of that. Now, why do we write it with the hyperbolic sine and cosine? Why not? The, whoops, that should be hyperbolic sine in there. Not just a sine. So hyperbolic sine has a combination of an e to the something and an e to the negative something. So writing it this way is just another way to write it with e with that exponent. So it's a little bit easier to write it with, since our exponent's a fraction, to not try to cram the fraction into an exponent, that we just write it more in this way to make it a little bit easier to read, potentially. So when we go ahead and find our u sub n, and this is going to be for by both x and y, we get this. Our fundamental set of solutions based on our ends. Notice that our y portion is the traditional sine cosine. So here we're going to mix an exponential with the trig. So whenever we combine it together, we get our summation. And I said I need parentheses for this. C value. Then times our u sub n's. And if we look back at our initial equations that we had here specifically, when our x value equals a, so whenever we're on this right-hand portion of it, we get some function of y. There's going to be our function that's f of y. So put this portion out front for any n value, n pi a over b is fixed. And then we apply the hyperbolic sign, we multiply by our c sub n. So that's a coefficient for our sine value that's going to have the y that we're controlling. So if we try to solve for the c sub n, and we can include that hyperbolic sign with it, if we really want our c sub n, we can divide by it. But if you think of it, really, this is one big constant that we're identifying. Oops. We're not doing those anymore. In this case, our function is a function of y, so we're doing all kinds of y's thrown in there. But if our f of y is based on the sum of sines, like we had over here, that it's based on a bunch of sine functions. So it's going to be an odd function. So, and then sine here is going to be an odd function. So it's an odd function times an odd function. That makes it an even function. So we can do a little bit of a shortcut in simplification for that. And now our C sub n, whenever we divide this portion over, our whole setup is going to have a over another hyperbolic. So we'll have a hyperbolic sine n pi x, looking back at the original. Over this. So whenever we're not talking about just our f of y, we're looking at overall u, our C sub n's are going to have this in the denominator. And whenever we plug in the original, it's kind of multiply to get that. This is going to simplify almost roughly when our n's are really, really big, at least. We can simplify this down to a 1/2 e the n by x over b, because the other part, it has the negative, or e to the negative n pi x over b. Whenever n's big, that whole thing's going to get really, really tiny. That should be a here. Pi a over b. There we go. And this one, our 1/2 will cancel. And then we can subtract our exponents. They both have an n pi b minus a. Or if you want to rewrite it, we factor out a negative there. And so since we write it with the explicit negative exponential, it will converge unless this a minus x is a really small value. So the closer we get to a, the more issues we'll have. But away from a, we have a nice solution. There's also the Dirichlet problem. Circle. So this is going to change things up a bit, because we're no longer dealing necessarily with our x's and y's. We now have r's and thetas. So we change it to a polar coordinate type deal. So our r is going to be between 0 and some a. Our theta is going to be between 0 and 2 pi. If we want to think of it as an initial condition with our theta being 0, excuse me, at a, so at our on the edge of the circle, we have some function of theta. Again, where theta is between 0 and 2 pi. And then we're going to have a nice periodic behavior So f of 0 will be the same as f of 2 pi, so f because the whole rotation around. So this equation will be bounded and let's r being less than or equal to a, and it's periodic for theta, with our period being 2 pi. And so my letters don't run together. So to draw a picture of this, we have our circle. This distance here will be a. That will be our theta. Along the boundary there, we have our f of theta, which is the same as u of a theta. And then here in the middle, so we have our u, r plus 1 over r sub r plus 1 over r squared. Second derivative for theta. And like before, we can assume that it's separable. So we get some function of r and some function of theta. So whenever we write our equation here, we're down to there, and it's still equal to 0. Now, if we make this separable, we end up with make my r connect a little bit better. And then lambda is going to be our separation constant. Now, if we take the individual ones and we multiply across to get rid of the fractions, then we set it, change it. We're going to get a set up like this. Oops, that should be a minus. And so we have two equations to solve. Now we have different cases depending on whether our lambda is positive, negative, or exactly 0. So let's look at what happens when lambda is less than 0. So say our lambda equals some negative u squared, where mu is greater than 0. So we have this, which if we substitute, we get down to there. So whenever we solve, we have that. But we said we want this to be periodic. So it's only going to be periodic if our whole function equals 0. So trivial solution. Let's try this equaling 0. If we do that, we get down to this. But our C2 is going to turn out to be 0, so that's gone. So we're only left with this part of it. Okay, that's doable. Let's look at our R's. Those are lambda 0, so we're not going to have the last part of this. And so our R equation turns out to be this. So, but this will not be bounded as R goes to 0, and we need to be bounded for all R's less than A, because our natural log will mess that up. So that means our K2 has to be 0. So our function for U is some C1 times a K1, or K1 times C1, depending on the order you want to do it in. So it's a constant times a constant. We can then choose our constants. So it equals 1. So non-trivial, but not exactly exciting. Let's see what happens when our lambda is greater than 0. So let's say lambda equals some mu squared value where mu is positive. R double prime and then R theta we're solving these. Our R comes down to this. Now we can't do our normal quadratic stuff on this for the R's because we don't have constants in front. We have that variable. But solving for this, it's an Euler equation, and it comes down to this. And then our theta is that. Now, as our R goes to 0, that part goes to 0. Excuse me, as our R goes to 0, this part will go to infinity because it's a 1 over. So we can't have that. So our K2 has to be a 0. So if we combine all of this together, it's again an R times a theta. So we're going to get this. Yet. The book starts with cosine. It doesn't really matter which way we do it. And this is almost kind of like the Fourier, except we have a extra variable in there. Change. Although for any given R, that and then that would combine just to be another constant. So it's very similar to the Fourier setup. And now if we take our function at A, we get that, which is going to be some straight function of theta, with theta being between 0 and 2 pi, but our f of theta plus 2 pi isn't equal f of theta. So we have that periodic behavior. And now we can solve for both C sub n and K sub n. And it should be a 2 over 2 pi out front, but they're going to simplify. And then the a to the n, K sub n, the same thing, just different, making sure those look like O's. Now that f theta has both cosines and sines in there, so we part of that did will cancel out to a 0. Cosine times sine will be odd, so that'll disappear. The cosine times cosine remains even, so that'll stay. The sine times cosine again for the bottom one again will be odd, so that will disappear. The sine times sine becomes even, so that sticks around. And then if we really want to solve just for the c or the n, all we have to do is divide by the a to the n's. Now this top one is going to be good for n equals 0, 1, 2, 3, and so on, because we need the c sub 0 out front, like we did with our Fourier before. And the bottom one is just going to be 1, 2, 3, and so on, because there's no k sub 0. But you can see how all of this tied together with our Laplace stuff and our Fourier stuff, all blending together to help solve some of these equations.